Let us begin by settling into the motivation for Lebesgue measure. It is helpful, at the very start, to recall why we felt the need to go beyond classical notions of length in the first place. In elementary analysis, length is something we associate very naturally with intervals. An interval has a beginning, an end, and the distance between them feels concrete and intuitive. For a long time, this intuition serves us well. We can measure segments, combine them, and reason about their size without difficulty. However, as analysis becomes more refined, we begin to encounter sets that are not intervals. Some are formed by taking infinitely many pieces. Some are highly fragmented. Some arise naturally when we study limits, convergence, or oscillatory behavior. For these sets, classical length becomes inadequate. It is either undefined, or it behaves in ways that conflict with our expectations. So the motivation for Lebesgue measure is not to abandon intuition, but to protect it. We want a concept of size that still agrees with length on simple sets, like intervals, but that also behaves well under limits, under countable operations, and under the kinds of constructions that naturally arise in modern analysis. We want a notion of size that is flexible, robust, and stable. It is reassuring to keep in mind that nothing radical is happening all at once. The construction of Lebesgue measure proceeds carefully, step by step, always checking that intuition is respected where it should be. Whenever we measure something familiar, we recover the familiar answer. The novelty only appears when we move beyond what classical tools could handle. Let us now move slowly toward the idea of outer measure. Outer measure is best thought of as a first approximation of size. It is deliberately generous. It does not yet insist on precision. Instead, it asks a simpler question: how small can we make the total length of intervals that cover a given set? Imagine you have a complicated set on the real line. Rather than trying to measure it directly, you allow yourself to cover it using intervals. You do not demand that these intervals fit perfectly. You allow overlaps. You allow inefficiency. You only ask that the entire set be contained inside them. Then you look at the total length of all those intervals. Now comes the key idea. You consider all possible such coverings, and you look for the smallest total length you can achieve. This smallest possible value, or more precisely the greatest lower bound of all such totals, is what we call the outer measure of the set. It is important to pause here and notice how natural this is. We are not measuring the set directly. We are measuring how tightly it can be surrounded by simple objects whose size we already understand. In this way, outer measure always exists. Every set can be covered by intervals, and so every set receives an outer measure. Outer measure has a few essential properties. If one set is contained in another, then its outer measure is no larger. This is monotonicity, and it aligns perfectly with intuition. Also, the outer measure of a countable union of sets is no greater than the sum of the outer measures. This is called countable subadditivity. It reflects the idea that covering many sets together should not cost more than covering them separately. At this stage, it is important to emphasize that outer measure comes before measurability. We do not yet decide which sets are well behaved. We first assign this rough notion of size to all sets. Only afterward do we decide which sets interact well with this notion. This brings us gently to the idea of measurability. A set is considered measurable in this framework if it behaves consistently with respect to outer measure when we split other sets using it. In plain language, a measurable set is one that cleanly separates size. Suppose you have any set at all, and you split it into two parts, the part inside a given set and the part outside it. If the outer measure of the whole equals the sum of the outer measures of the two parts, then the splitting is compatible with measurement. If this holds for every set you try to split, then the set doing the splitting is called measurable. It is helpful to think about this repeatedly. Measurability is not about the internal structure of a set. It is about how the set interacts with all other sets. A measurable set does not distort size when used as a divider. At this point, one might wonder why not simply declare all sets measurable. The answer is subtle but important. Some sets are so irregular that they destroy the consistency of measurement. If we allowed them, basic properties like additivity would fail. Measure theory chooses discipline over excess. It includes as many sets as possible, but not more than that. The collection of all measurable sets forms what we call an extended sigma algebra. This is simply a collection of sets closed under complements and countable unions chosen so that outer measure becomes a true measure on this collection. The language may sound abstract, but the idea is calm and reasonable. We are selecting the largest family of sets on which size behaves as it should. With this in place, we can now describe the construction of Lebesgue measure itself. We begin with intervals because they are the simplest objects whose size we trust. We assign to each interval its intuitive length. From there, we consider open sets, which are countable unions of intervals. Their size is naturally defined as the sum of the lengths of those intervals. Next come Borel sets. These are sets generated from open sets by repeatedly taking complements and countable unions. Borel sets already cover most sets encountered in analysis. However, Lebesgue measure goes slightly further. By completing the measure, we also include all subsets of sets of measure 0. The result is the collection of Lebesgue measurable sets. This is the largest reasonable collection of sets for which length behaves consistently. It includes all familiar sets and many unfamiliar ones, but it deliberately excludes pathological constructions that would break the theory. It is worth resting here for a moment. The construction may sound elaborate, but it is guided entirely by intuition. Start with what you trust, extend carefully, and stop before contradictions appear. Now let us reflect on the properties of Lebesgue measure. One of the most important is translation invariance. In words, this means that if you shift a set along the real line, its measure does not change. Length does not depend on location. This is a deep expression of geometric intuition, and it holds perfectly for Lebesgue measure. Another key property is completeness. If a set has measure 0, then every subset of it is also measurable and has measure 0. This matters because sets of measure 0 often arise as exceptional cases, and we want to be free to ignore their internal complexity. Throughout all of this, Lebesgue measure remains consistent with geometric intuition. Intervals have the expected size. Disjoint sets add their sizes. Shifts preserve size. Nothing surprising happens where it should not. Let us now transition calmly and gently to Lebesgue Stieltjes measure. The motivation here is not to replace Lebesgue measure, but to generalize it. Instead of measuring size according to length alone, we measure size according to how a given function accumulates. Imagine a function that increases as you move along the real line. This function represents accumulated weight, mass, or probability. The idea of Lebesgue Stieltjes measure is to define size in terms of the increase of this function. Different growth patterns lead to different measures. A function that grows steadily leads to something resembling length. A function with jumps leads to measures that assign mass at specific point. A smooth function leads to a smoothly distributed measure. This is not a complication. It is a unification. Lebesgue measure becomes a special case where the function grows uniformly. When assigning size to intervals, the Lebesgue Stieltjes measure looks at how much a function increases across the interval. If the function jumps, the interval captures that jump. If the function grows continuously, the size reflects that growth. It is helpful to think again about step functions. Each jump contributes a discrete amount of measure. Smooth growth spreads measure continuously. Both behaviors coexist naturally in this framework. Now let us gently recall Riemann integration. In Riemann integration, we partition an interval into small pieces, evaluate the function on each piece, multiply by the width, and sum the results. The idea is to approximate area by rectangles. Riemann-Stieltjes integration modifies this idea by weighting each piece according to the change in another function. Instead of multiplying by width alone, we multiply by the increase of a function. This allows us to integrate with respect to distributions that are not uniform. Again, intuition is central. We are accumulating values, but the accumulation depends on how mass is distributed. Lebesgue integration takes a further step back. Instead of slicing the domain into intervals, it groups together points where the function takes similar values and measures the size of those groups. Integration becomes summation with respect to a measure, rather than summation with respect to length. This perspective explains why Lebesgue integration is so powerful. It adapts naturally to limits, to convergence, and to regular behavior. When functions are well behaved, all these integrals agree. When functions become more complicated, Lebesgue integration continues to work where earlier methods fail. This is not a loss of classical results, but their preservation within a broader framework. Finally, let us reflect on integrability conditions. A function is Riemann integrable if its discontinuities are limited in a precise way. A function is Lebesgue integrable if its size, weighted by the measure, is controlled. Boundedness, continuity, and the structure of discontinuities all play a role. It is helpful to return again and again to the idea of control. Integrability is about preventing mass from escaping to infinity. Lebesgue integration gives us tools to manage this carefully. As we conclude, let us rest with a unifying thought. Lebesgue measure and Lebesgue-Stieltjes measure extend classical ideas of size and accumulation without discarding them. They provide a consistent, and flexible framework that supports probability theory, stochastic processes, and modern analysis. They allow us to measure, integrate, and reason about complexity while preserving intuition.